Welcome to Energy Session 2.0, Renewable Energy, Solar PV. This EMSI training section covers renewable energy, specifically for solar PV. Your presenter is Rick Mitchell. Renewable energy refers to the sustainable and inexhaustible energy resources such as solar, wind, hydro, geothermal, and biomass, which occur naturally on Earth. Renewable energy technologies, often referred to as RETs, are generally efficient and non-polluting. They are also essential for reducing Australia's greenhouse gas emissions and securing our energy supply into the future as fossil fuels become scarcer and more expensive. Here we'll look at solar PV as the most accessible and commercially viable option for residential and small enterprises. Solar energy from the sun is derived in two forms. Firstly, as heat, which can be captured to boil water using solar thermal systems, and secondly, as radiated light, which can be converted into electrical energy using solar photovoltaic systems, or solar PV, as it is commonly referred to. Photovoltaic cells exploit the photovoltaic effect, that is, the properties of certain materials to generate electrical power when directly hit by rays of the sun. The advantages of harnessing solar energy are that it reduces emissions of greenhouse gases by supplementing traditional fossil fuel energies, reduces the need for power transmission lines as it can be produced off-grid, preserves land, water, and natural ecosystem services two ways, because there is no large-scale extractive process, like mining, needed to accumulate the resource, and because unlike fossil fuels, it doesn't produce smoke, gas, and chemical byproducts, protecting the surrounding environment from pollution. It also speeds up the rural electrification process, and there are a number of social benefits associated with the development of solar PV. The main disadvantages of solar PV at this point in time are the cost of initial installation, variable performance with respect to different geographic locations and the number of sun hours a certain location receives per day and throughout the year, inefficiency in energy storage technologies, and the chance of damage in extreme weather events which large areas of Australia are prone to. So what is a solar PV system? A grid-connected solar PV system is an array of photovoltaic modules connected via an inverter to provide power for your home or business where excess production is fed into the grid. Standalone PV systems are not connected to the main supply or power grid. They are good for rural or isolated areas with no grid power, but they require a deep cycle rechargeable battery to store electricity. And if the battery bank has nominal voltage of 120 volts DC or above, maintenance can only be undertaken by a suitably licensed electrical worker or contractor. To properly understand the potential benefits of solar PV, we will address four key topics: solar PV system components, solar PV system design, calculating solar PV system output, and calculating STC entitlements. PV system components. Let's start by looking at the system components. It all starts with solar PV cell. Photovoltaic cells are semiconductor devices capable of converting sunlight into direct current, DC, resulting in electricity. The direct current is carried through wiring to an inverter, which converts the current to alternating current, allowing it to be connected to a property's main electricity distribution board. You can see in the diagram here that the term solar panels may refer to solar PV cells, solar modules, and/or solar arrays. To disambiguate the diagram, cells are the semiconductor devices that convert sunlight into direct current electricity. Modules consist of PV cell circuits sealed in an environmentally protective laminate and are the fundamental building blocks of PV systems. Panels include one or more PV modules assembled as a pre-wired field installable unit. An array is the complete power generating unit consisting of any number of PV modules and panels. So how do solar cells work? Well, when sunlight strikes the surface of a PV cell, the photovoltaic effect takes place. The photovoltaic effect essentially equals photons in and electrons out. A thin wafer consisting of an ultra-thin layer of phosphorus-doped silicon on top of a thicker layer of boron-doped silicon facilitate this process. The electrical field provides momentum and direction to light-stimulated electrons, resulting in a flow of current when the cell is connected to an electrical load. A typical PV cell with a surface area of about 160 centimeters squared has the capacity to produce about 2 watts. The material that a solar cell is made from has a dramatic effect on energy generation, from the energy used in the manufacturing process to the energy produced by the cell. PV cells vary based on the crystallinity, band gap, absorption, and manufacturing complexity. Monocrystalline silicon cells get their name from the fact that the silicon wafer is cut from a single crystal of silicon. Silicon is grown in a laboratory and is then sliced thinly into wafers. Monocrystalline silicon cells are generally the most efficient PV cells and produce the smallest size solar cells, meaning they maximize efficiency. Due to higher production costs, monocrystalline cells tend to retail for a higher price than other technologies. Further to this, they don't perform as well as polycrystalline cells or thin films under higher temperatures over 25 degrees Celsius. Polycrystalline silicon cells, also known as multicrystalline, are cut into thin wafers from a block of melted and recrystallized silicon and assembled into complete cells. Polycrystalline silicon cells are the most popular choice as they provide the best balance of performance and cost. Though they are not as efficient as the monocrystalline cells, they are cheaper to produce and source. However, recent improvements in polycrystalline technology are slowly bringing it closer to monocrystalline in terms of size, efficiency, and heat tolerance. Polycrystalline are the European standard. Amorphous or thin film silicon cells are made up of silicon atoms in a thin layer rather than a crystal structure. They can absorb light more readily than crystalline silicon, so the cells can be thinner and they use the least amount of silicon. While generally less efficient, there have been technological advancements, meaning some panels can now generate efficiency up to nearly 12%. They offer the best shade tolerance of any solar technology and perform better under hotter conditions. The biggest drawback of the thin film is that they require about twice the roof space to achieve the same power output as a similar crystalline panel. In addition to the solar cells themselves, there are a number of other components used in the installation and running of a solar PV system. Racking refers to the racks or mounts that solar panels are mounted on. Most homeowners and small to medium businesses will install solar panels on their roofs, although ground-mounted panels are also an option in some circumstances. The structures used to mount solar panels onto a roof come in a variety of styles depending on a building's requirements. Fixed mounting is the most simple and least expensive type of solar panel mounting system. The solar panels should always face the equator, due north in the southern hemisphere. Don't forget though that true north varies from magnetic north, and this can make a huge difference. The angle of inclination in degrees should be set to about your latitude, and this will be covered in more depth shortly. Adjustable mountings allow you to manually adjust the angle of inclination of a solar array to respond to the sun's position. This will account for the lower angle of the sun in winter and the higher angle in summer, as the Earth orbits the sun, causing seasonal change. A good rule of thumb to determine the optimal angle is latitude plus 15 degrees in the winter and latitude minus 10 degrees in the summer. Generally, you would do this for the winter position in about mid-March and back to a summer position in mid-October. This can increase overall solar panel output by approximately 25%. Tracking or automated mountings follow the path of the sun during the day to maximize the solar radiation that the solar panels receive. A single-axis tracker tracks the sun only in an east to west movement, whereas a dual-axis tracker tracks the seasonal movement of the sun in addition to the daily east to west movement. Though this is the most effective system in terms of maximizing solar exposure, it is also the most expensive. However, in some instances, the 20 to 30% increase in efficiency can outweigh the capital expenditure. But you would have to complete a detailed cost analysis to ensure this, because generally at 2012 prices, one could instead buy 25% more panels, cheaper, and have the same increase in power with no mechanical failures to worry about. Cabling, as with all component parts, is largely the responsibility of the installer. However, it is important to know that losses which occur through cabling can compound into losses in energy supply. Generally, thicker wire, more insulation, and lower spans equate to higher energy retention. The next system component we will look at is the inverter. Inverters are a crucial component of the system as they receive the DC power supply and convert it into AC power, creating useful electricity. The inverter converts DC into 240 volt alternating current, or AC current, which is suitable for your household appliances and for feeding into the grid. The supply of direct current is variable, dependent on the sun and other factors. The electricity, once it has been converted into AC, is then fed into the commercial electrical grid or local, off-grid electrical network. The efficiency of an inverter is measured by how well it converts DC electricity into AC electricity. Usually this is 95 to 97.5% for most models. Maximum power point tracking is a system that inverters and solar battery chargers use to get the maximum power from the solar panels. The purpose of the MPPT system is to sample the output of the cells and apply the proper resistance load to obtain maximum power for any given environmental conditions. MPPT needs continual recalculation to extract the optimal power output based on variables such as the time of day. Each solar cell has a point at which the current and voltage output from the cell result in the maximum power output of that cell. The principle is that if the output from the cell can be regulated to the voltage and current levels needed to achieve a power output at this ideal point, then the power generated by the solar cell will be used most efficiently. Maximum power point trackers find the optimal power output automatically by finding the peak of the green curve which represents power. MPPT ensures that you get the most power possible from your solar panels at any point in time. It is particularly effective during low light level conditions. These calculations result in an output that delivers maximum current at the required voltage at any point in time. Though not integral to the operation of the system, metering performs an important function in quantifying the amount of electricity generated by the system or delivered to the grid. This is necessary for billing and system maintenance and operation reviews. Metering for this purpose is commonly done with the inverter unit, but there are a number of other metering opportunities that households and businesses can take advantage of to increase efficiency in both solar energy generation and regular business operation. Metering provides a means to change the way households and small businesses use electrical appliances by making energy use visible to staff and household members. This provides a potential means to reduce operating costs and greenhouse gas emissions. With intelligent metering, some households and firms have found savings of up to 20 to 30% with little or no investment, simply through increasing awareness. There are two main types of metering opportunities applicable at this scale: smart web metering and appliance energy meters. Smart or web meters record energy consumption or generation in much the same way as the meter in an inverter does. However, the distinct advantage of web metering is that the information is sent to a monitoring site that displays energy use or generation information in relatable terms. Clients can use this engaging format to monitor their energy use live, and this is a great educational tool for businesses to use with their staff. In addition to measuring energy used, electronic meters can also record other parameters of the load and supply, such as maximum demand, power factor, and reactive power used. They can also support time of day billing, for example, recording the amount of energy used during on-peak and off-peak hours. Smart web meters can be fitted to main or multiple sub-circuits, allowing them to report on any level of information required, though obviously the more circuits it is fitted to, the more detailed the information reported, and the more opportunity for efficiency. You can also connect appliances directly into monitoring equipment to record the specific power use of individual appliances. There are a variety of models available on the market today, but they all work on the same basic principle. The meter is plugged into an outlet, and the appliance to be measured is plugged into the meter. Such meters can help in energy conservation by identifying major energy users or devices that consume excessive standby power. Solar panels, being roof-mounted electrical devices, also require a certain level of protection. Components such as fuses, circuit breakers, and AC isolators act as anti-islanding protection. Battery banks are necessary in standalone solar PV systems to store the electrical energy generated. A generator and battery charger are usually part of a standalone system, so that in events of extended bad weather, you have a backup supply which helps safeguard your batteries. If you try to use more electrical energy than the battery bank holds, you will run the batteries too low and reduce their life expectancy. A hybrid system is a solar system that includes a LPG, diesel or petrol generator or wind turbine to help generate power to the battery bank, alongside or as an alternative to the solar PV generation. Reducing BOS costs can be a challenge. Each PV system has unique characteristics as it is individually designed. Opportunities for cost reduction do exist relating to improving technology, more appropriate regulations, better information, or economies of skill and scale. However, Efficient systems design whereby unnecessary cabling is avoided, natural cooling and protection of system components is considered, and the education of clients on correct usage is achieved, will reduce costs and increase the power output of the system. Reducing BOS costs can be a challenge. Each PV system has unique characteristics as it is individually designed. Opportunities for cost reduction do exist relating to improving technology, more appropriate regulations, better information, or economies of skill and scale. However, efficient systems design whereby unnecessary cabling is avoided, natural cooling and protection of system components is considered, and the education of clients on correct usage is achieved, will reduce costs and increase the power output of the system. Solar PV system design. The design of a solar PV system centers on the need for solar access, suitable kilowatt capacity, the impact of orientation and shade on output, as well as determining the expected kilowatt hours supplied by the system and subsequent small-scale technology certificates, or STCs, that can be generated. Solar access refers to the amount of sun's energy available to a building based on its orientation and the orientation of its potential solar arrays. Establishing good solar access results in maximum use of free solar energy. Shading has a big impact on solar panel output and is generalized into two categories. Soft source shading is defined as diffused or dispersed shading, caused by objects such as tree branches which shade from a distance. Hard shading sources are defined as those that stop light from hitting the cells, such as a blanket or tree branch sitting directly on top of the panels. As the diagram shows, even if one full cell is hard shaded, the voltage of that module will drop to half of its unshaded value. If enough cells are hard shaded across each of the series, the module will not convert any energy and will become a tiny drain of energy on the entire system. When a full cell is shaded, it can consume energy produced by the remainder of the cells which aren't shaded, triggering the module to protect itself. Consider this diagram, where a solar array is illustrated containing a number of solar cells. Each cell produces approximately 0.6 volts, meaning if there is no shade on the panels, the 60 cells would output 36 volts. The cells are connected in 3 series of 20, and each series contains a bypass diode which will bypass that group of cells if any of the cells are in hard shade, and therefore not producing a voltage. So in the first diagram, 1/3 of the output is cut out by shading just 2 or so cells. Hard shade on just 6 cells of a 60-cell panel can shut down the panel completely. Hard or soft shading is also affected by the position of the sun, relevant to the solar panel and obstacle. The higher summer sun may not be obstructed by a tree that blocks the lower winter sun. A general rule of thumb regarding solar access and shading is that no shading should be present in the key daylight hours between 9 AM and 3 to 4 PM within plus or minus 60 degrees north. If the main loads are in winter months when solar availability is reduced, tilt angles should be more vertical, approximately equal to latitude plus 15 degrees to maximize exposure to the low winter sun. If the major loads are in summer because the client has refrigeration or air conditioning processes, then the tilt angle should be reduced to approximately latitude minus 10 degrees. This is where adjustable mounts are useful to be able to capture the most sun in both summer and winter. The maximum sustained output of a solar panel is determined under standard test conditions. Essentially, solar panels are put through a flash tester in the manufacturing factory that has been calibrated to deliver the equivalent of 25 degrees Celsius, which is quite unrealistic in Australia, where the panel temperature under typical conditions in summer can reach 70 degrees Celsius in a radiance of 1000 watts per meter squared, meaning the orientation and shading is perfect and assume an air mass of 1.5. These conditions correspond to a clear day with direct sunlight on the solar panels. Under these test conditions, a solar cell of 20% efficiency with a 100 centimeter squared surface area would produce 2.0 watts of power. Solar cells are designed to operate at peak power at around 25 degrees Celsius. This figure shows that a higher voltage is induced when there is cooler temperatures. Therefore, higher generation of power can be achieved when the cells are mounted in a way that allows wind flow under them for cooling. Another consideration is wind loading. By allowing air to flow around these solar panels, they will remain cooler, but also the wind resistance of the entire array is less. The efficiency of panels is affected by construction, shade and orientation, location, temperature, and a host of other variables, which means that no two panels anywhere in the world will operate identically. However, to standardize measurements across the world, the unit peak sunlight hours is used, with 1 peak sunlight hour representing the sun's ability to deliver 1000 watts per meter square for 1 hour. PV system output energy is based on peak sun hours, which is a measure of the available solar energy that occurs at a given location. For example, if an area receives 6 peak sun hours, it means that the energy received during total daylight hours at that location equals the energy that would have been received had the irradiance for 6 hours been a constant 1000 watts per meter squared. Peak sun hours varies throughout the year based on movement of the sun, subsequent climate, weather, and location, and is usually averaged and presented as a monthly figure. This table shows the monthly and annually peak sun hours for Brisbane, Melbourne, and Sydney. Output over the year will vary in line with the monthly sun hours as shown in the table. This table provides data showing the average daily electricity output of some common grid-connected systems throughout Australia. According to the Clean Energy Council of Australia, the most common household systems are either 1 or 1.5 kilowatts. The first step in designing a solar PV system is to determine the client's requirements, specifically regarding the level of energy reduction they are targeting. This may be based on a desire to reduce expenditure on electricity bills, environmental benefits, or have backup power, all considered in the context of their budget. You should ask, is there a match between expectations and outcomes? Has the client budgeted for a system that will serve their needs? And what sort of payback period are they looking at? To make recommendations on the size of system that might be required, you simply have to quantify the client's daily load. This is the average daily energy use of the premise. You can find this information on your client's energy bills or use the value that you calculate at the end of your audit. This table, sourced from research done by the Alternative Technology Association in 2011, estimates the payback periods for installation of a solar PV system within various states of Australia. Notice that different states and territories receive different amounts for the electricity they feed into the grid through the various feed-in tariffs. The scenario is based on a 1.5 kilowatt system that fully installed would cost roughly $8,250 before payment of small-scale technology certificates. Now let's look how we can perform a basic calculation to determine solar PV system's output. The equation used to determine the energy output for a solar PV system states that the average daily energy output of the PV grid system is equal to the product of the average daily energy output of the PV array in watt hours, the efficiency of the inverter, and the losses in the system cabling. In the equation, E array is the product of a number of factors including derating factors and peak sun hours, which all respond to the efficiency of the system. In an audit situation, it shouldn't be necessary to perform these calculations, but it's good to know the contributing factors to the eventual energy output of a PV system. To perform a basic on-site calculation without accounting for losses, we can simply multiply the rated output power, number of panels, peak sunlight hours, and efficiency of the inverter. For example, let's say you are considering installing 27 panels, each with a rated output power of 180 watts peak in Brisbane. Using the shortened formula, apply the peak sunlight hours for Brisbane, which is 5.4, sourced from the table earlier in the presentation, and inverter efficiency, which is 0.97. This tells us the solar PV system would generate 25.45 kilowatt hours on an average day under peak conditions, not accounting for losses. Example 2. A customer uses 550 kilowatt hours of AC power per month, on average, at their home and wants a solar system that will produce 100% of their power over the year. First, we'll convert the monthly power usage to daily. 550 kilowatt hours per month is equal to 18.33 kilowatt hours per day, when assuming a 30-day month. To this, we'll divide by the peak sun hours, that is, the number of hours the system will likely be in operation, to convert back into kilowatts. Here we'll use 5.5 as the statistical average peak sun hours for all of Australia. Assuming the roof is perfectly placed to harvest 100% of this 5.5 sun hours each day, and temperature loss is insignificant, we get 3.33 kilowatts required to be produced each day. However, this is still DC, and will have to be converted into AC to be useful. The standard rule of thumb is a drop in efficiency of 20% in the process of converting from DC to AC. So here we divide the kilowatt AC requirement by 0.8 to equal 4.16 kilowatts. This means that if a customer wanted to produce 100% power from solar energy in Australia, and they had a perfect roof, a solar system that can deliver 4.16 kilowatt DC power would be needed. Remember here that we are not accounting for a backup supply in the event of cloudy days or electricity use out of sunlight hours. Thus, a storage system such as batteries would be required to increase the level of self-sufficiency from the electricity grid. State feed-in tariffs. Feed-in tariffs, or FIT schemes, are a premium rate paid for electricity fed back into the electricity grid from a renewable electricity generation source. Feed-in tariffs are a way of subsidizing renewable energy and can be implemented in conjunction with mandatory renewable energy targets. FIT schemes are a policy mechanism designed to accelerate investment in renewable energy technologies. There are two main types of feed-in tariffs applied, dependent on where you are located in Australia. A net feed-in tariff, also known as export metering, pays the PV system owner only for surplus energy they produce, whereas a gross feed-in tariff pays for each kilowatt hour produced by a grid-connected system. It's a very important difference. Net feed-in tariffs pay the PV system owner only for surplus energy they produce. In this diagram, the blue section represents the energy use of a working family household, with peak power use clearly depicted by the two spikes. The area in yellow shows the amount of solar-generated energy used by the house itself, and the green represents the excess energy that the household can sell back to the grid at a profit. Considering that same household under a gross feed-in tariff, which pays for each kilowatt hour produced by a grid-connected system, results in a graph that looks like this, where the total energy generated is metered before entering the house to be used in calculating the total gross profit. You can see the obvious benefits here when the section that was once yellow, depicting the number of kilowatts used by the house, is now added to the total kilowatts used to calculate profits. The table above shows the different feed-in tariff rates, tariff models, and status of schemes in each state and territory in Australia at October 2012. As we covered in the introductory session 2.0 legislation, small-scale technology certificates are a measurement of renewable energy which can be traded for a monetary value. The STC and LGC schemes cover three types of systems: solar water heaters and heat pumps, small generation units, either solar PV systems, small wind systems, small hydro systems, or small biomass systems, and power stations, medium to large scale systems, for example, large wind turbines. Unlike the first two categories, power stations create STCs on an ongoing basis. Green energy trading cannot create STCs for these systems. Instead, they must register with the Clean Energy Regulator. The amount of small-scale technology certificates each solar PV system is eligible for varies and depends on two factors. 1. The size of the system, and 2. The location, as the number of peak sunlight hours varies across Australia. Small-scale technology certificates for small generating units are created in batches known as Deeming Periods. The Deeming Period is an estimate of the number of years a PV system will generate renewable energy. Owners of solar PV SGUs can choose to create STCs cover 1, 5, or 15-year Deeming Periods depending on the particular installation. If STCs are chosen to be created annually, this occurs at the start of each year on the date of installation. For 5-year Deeming Periods, STCs are created on installation for the first 5 years after installation, and then at the start of each subsequent 5-year Deeming Period. If the 15-year Deeming Period is chosen, STCs are created on installation with no further Deeming Periods available for that SGU. The 15-year Deeming Period option is only available within 12 months of the installation date. There is a simple 4-step system to determining how many STCs may be created for a solar PV system. Australia has been divided into 4 zones for solar PV and installations, which represent the differing number of sunlight hours across Australia. Establish your zone by using Table 2, ratings and postcode zones for small solar photovoltaic systems on the upcoming slide. 2. Once you have established your zone, look up the corresponding zone rating in Table 3. These tables can be used to determine the zone ratings for solar PV systems based on their location. For example, if your client lives in Sydney City with a postcode of 2000. Table 2 states that postcodes between 1001 and 2356 correspond to Zone 3. And Table 3 tells us that Zone 3 has a rating of 1.382. So we know now that the zone rating for a Sydney City resident is 1.382. Step 3 is to calculate the system's annual STC entitlement by multiplying the zone rating by the rated power output in kilowatts of the PV system, which you can find in the specifications provided by the manufacturer. Be sure to use the exact figure that applies to the particular model. You should also note that if a system is entitled to more than 250 STCs per year, the system is classified as a potential PV power station. This would mean that the system owner must apply to the Clean Energy Regulator to become an accredited power station to be entitled to large-scale generation certificates. Step 4 is to calculate the STC entitlement for each deeming period by multiplying the annual STC entitlement, calculated in Step 3, by the number of years in the deeming period you choose, 1, 5, or 15. If your calculation yields a decimal number, you must round down the nearest whole number. For example, if the calculated STCs is 82.88, the actual number you are entitled to is 82. The Federal Solar Credit Scheme provides additional support to households, businesses, and community groups that install small renewable energy generation units, such as rooftop solar panels and small-scale wind and hydroelectricity systems. Solar credits increases the number of STCs that can be credited for eligible installations of small-scale solar panel, photovoltaic, wind, and hydro systems. They work by multiplying the number of certificates that these systems would generally be eligible to create under the standard deeming arrangements. The level of support in terms of the number of certificates received via solar credits will be determined by the date the system is installed. The solar credits multiplier applies to the first 1.5 kilowatts of capacity for systems connected to a main electricity grid and up to the first 20 kilowatts of capacity for off-grid systems. There is no cap on the number of STCs that can be created. On 5th of May 2011, the Australian government announced that the solar credits multiplier would be reduced to 3 for small-scale systems installed from 1st of July 2011. The multiplier will phase down by 1 each year, consistent with the original intent of the solar credits multiplier reducing over time, until the multiplier is phased out by 1st of July 2013. So let's walk through an example. Say we want to calculate the STC's eligibility without the solar credit scheme for a client who has a PV system installed on the 8th of October 2012 in the postcode area of 4104, which has a rated power of 1.72 kilowatts under a 15-year deeming period. Firstly, we determine eligibility. Is the solar system installed within the last 12 months? Yes. Does the system have a rated output of 100 kilowatts or less, or a total annual output less than 250 megawatt hours? Yes. Was the system installed by an accredited installer? Yes. The system meets all the eligibility requirements, so we can now proceed to calculate the number of STCs the client is entitled to. The next step is to look up the postcode on Table 2 to find out what the Zone 4104 fits under. Table 3 tells us that the Zone 3 rating for solar equals 1.382. Now we have all of the information required to work out the client's annual STC entitlement. So the zone rating of 1.382 is multiplied by the rated power of 1.72 kilowatts, multiplied by the deeming period, which is 15. This equals 35.65 megawatt hours, which is rounded down to equate to 35 small-scale technology certificates. Now let's look at an example where we calculate STCs with solar credits. Let's use the same scenario. We want to calculate the STC's eligibility under the solar credit scheme for a client who has a PV system installed on the 8th of October 2012 in the postcode area of 4104, which has a rated power of 1.72 kilowatts under the 15-year deeming period. We need to remember that the solar credits multiplier only applies for the first 1.5 kilowatts of capacity installed with grid-connected systems at eligible premises. Generation capacity above 1.5 kilowatt either on the original unit or any additional capacity installed at a later date will be eligible for the standard 1-to-1 rate of STC creation. So we require two formulas. The first to calculate the STCs for the first 1.5 kilowatts, which is equal to the product of 1.5 kilowatts, the zone rating, deeming period, and solar credits multiplier. and secondly for the remaining solar PV output, being equal to the total output minus the initial 1.5 kilowatts, which is the product of the remaining output, the zone rating, and the deeming period. The zone rating is calculated in the same way as previous, using tables 1 and 2. And we know the deeming period is 15 years. And the total rated power is 1.72 kilowatts, which minus 1.5 is 0.22 kilowatts. Using the solar credits table, we know that the multiplier for works carried out between the 1st of July 2012 and the 13th of June 2013 is 2. Working through the equation, we come to 66.75, which, when rounded down, tells us that the system would generate 66 STCs. STCs are part of a larger class of certificates that is referred to as REC, Renewable Energy Certificate. It is a measurement of renewable energy which can be traded for a monetary value. One REC represents 1 megawatt hour of electricity. RECs cover both small-scale technology certificates and large-scale generation certificates. Every installation carried out by an accredited installer is required to meet the following Australian standards: AS477, Grid Connections of Energy Systems via Inverters; AS-NZS 3000, Electrical Wiring Rules; AS1768, Lightning Protection; AS-NZS 1170.2, Wind Loads; AS-NZS 5033, Installation of Photovoltaic PV Arrays. To continue with presentations, please select Energy Session 3.0, Electric Motors, from the navigation bar. To complete the assessment for this presentation, please select Tutorial 2.0, Renewable Energy Solar PV.